Thank you for the introduction. Good morning, everyone, and welcome to my presentation. This work has been done together with my supervisor, Professor Rosso, and Professor Bacchus. The main topic of my today's presentation will be JIT compilation and its consequences on the security of modern browsers. JIT, or just-in-time compilation, as you all know, is a process of converting a higher-level language into a native code at runtime. And more specifically, I will be looking at JavaScript JIT compilers, which are used in modern browsers to increase the performance of executed JavaScript code. And although it indeed increases the performance of JavaScript multiple times, it has few security issues which need to be considered. And to demonstrate one issue, I will use this simple visualization. If we assume that the attacker is in control of the JavaScript code, this means she can inject arbitrary values into the JavaScript. And now JIT compiler must make sure that these values do not end up in native code after compilation. Otherwise, this will be a clear code injection attack, which can later be reused in code reuse attacks. This type of code injection attacks has already been used in the past, and browser vendors are also aware of them. However, their defense techniques are not always complete, and in our work we will look at them and see if there are some remaining cases which need to be protected. However, before I go into more details, let me briefly go over code reuse and code injection attacks. In basic code reuse attack, as name suggests, attacker is supposed to reuse code from existing code pieces, and the steps that the attacker takes are the following. It first identifies the set of gadgets and functions that she wants to reuse, and then chains them together by writing their addresses on a stack, and also providing parameters, and finally jumps to the beginning of the gadget to trigger the execution of the whole sequence. And however, main requirement here is that attacker must know the addresses in advance in order to use the gadgets and functions. And this is not possible anymore because of most widely used defense technique, address space layout randomization. What it does is that it randomly shuffles memory segments in the address space to randomize the base addresses of memory pages. And by doing so, attacker cannot know where the gadgets are. And even to deal with single pointer leaks, many researchers suggest to use finer grained randomizations to randomize code inside code pages. However, in the context of JIT-compiled code, attacker doesn't really need to reuse existing code pieces. Instead, she can also inject her own code. And how this works can be demonstrated in this simple example. In the statement on the left, we have an assignment statement of JavaScript using integer constant and writing into a variable. And after JIT compilation, this will be converted into two assembly instructions, one of which is a move instruction, moving embedded value into a register. And however, embedded value is now taken from the value that was supplied by the attacker. And this type of assignments can be, or statements can be used for the attacker to do arbitrary 4-byte gadget injections. Or more advanced technique is to, instead of using single gadgets, to spray multiple of them together. By doing so, the attacker now is able to allocate most portion of address space, and then by randomly jumping at some address, she increases the chances that executed code will be actually the ones that she sprayed. However, all these techniques are already known to browsers, and they also try to defend against it. And one of the defense techniques that exist in Internet Explorer, Edge, and Chrome is constant blinding, in which instead of using single instruction to move an embedded value into a register, it is split into half. In the first instruction, original value XORed with a random key is moved into a register, and then another XOR instruction is used to restore the original content of the constant in a register. And now, although we have two embedded values emitted, none of them are under the control of the attacker, and both are random and cannot be predicted or calculated. There are still issues with this approach, and namely that constant blinding is only applied to constants that are larger than 2 bytes for performance reasons. And this was shown in the past that 2-byte constants are actually enough in Internet Explorer to do arbitrary code injection and arbitrary code execution. And also other fields of x86 instruction can also be used, such as displacement, to inject arbitrary 3-byte gadgets. In our work, however, we concentrate on the completeness of constant blinding itself. That is, we want to look at the values that was supposed to be blinded and to check if they are actually blinded after compilation. And we do this using the dynamic approach. We simply want to generate random JavaScript functions, compile them, and then compare native code with the initial JavaScript source code to see if there are similarities between embedded values and integer constants. To do this, we use the following framework called Dachshund, and it contains 3 main modules: controller, JavaScript fuzzer, and JIT inspector. Initially, controller will generate a random number and pass it to JavaScript fuzzer, which will generate a JavaScript function, contains this number as an integer constant in one or more of its statements, and then the generated function will be passed to browser for compilation. And in our case, by compilation, we mean 2 levels of compilers. The first is baseline compiler, which is supposed to work quickly and generate inefficient code. And then after this code has been executed multiple times, it will be recompiled again by optimizing compiler to make it more efficient. And we target both of these compilers to check if any of these compilers use non-blinded constants. And after compilation, then JIT inspector comes into play. We'll dump the memory of browsers, find the compiled function, identify embedded values, and check if the original constants that were coming from controller is present there. If such a value is found, it will be reported back to the controller as potential leak. Running this framework for a couple of hours already showed us a variety of different results where constant blinding is not applied. And these examples can be seen here, but it's not all. There are more of them. And the simplest one, for example, is returning an integer constant from function, which will actually generate embedded value into the compiled code. However, although this set of statements that use non-blinded constants look similar in both browsers, the reason why they are not blinded are different. In Chrome, we found out that we only see non-blinded constants in optimizing compilers, and this is probably because Chrome favors performance more and tends to not blind all of the constants in its optimizing compiler. However, because attacker can simply trigger optimization compiler by running the same function multiple times, she can also trigger generation of these gadgets. In Internet Explorer, however, we saw that both baseline and optimizing compiler would generate such gadgets. And in all of the cases, these gadgets were coming from the same place. And looking at the native code, this looks something like embedded value caching. And how it works is the following. Whenever you use an integer constant in JavaScript, instead of inlining it every time you want to use it, it will be first moved into a spare register at the beginning of the function. And then every time you use this constant, the register will be read. However, the problem here is that the initial storage of integer constant into a register is not blinded, and therefore attacker has a chance to do arbitrary 4-byte code injection per generated function. And as we all know, 3-byte gadgets are enough in x86 code to do arbitrary code execution, so having 4 bytes makes it more than enough. But still, I will demonstrate simply how the attacker is able to generate the following set of gadgets in both browsers. The set of gadgets is used to set parameters for virtual protect function, which is used to mark memory pages as executable in Windows. So to generate this set of gadgets in Chrome, we simply create a single function, use 3 different integer constants in it, and then call this function more than 1,000 times to trigger optimizing compiler. And it will trigger gadget generation. And in Edge, we have to generate 3 different functions, having each of the constant in one of these functions, and then executing them around 50 times to trigger baseline compiler. Seeing the threat that we can actually inject 4-byte values and into the code. Now we wanted to defend against it. And the problem here is that we see the threat in multiple browsers, in Edge, Internet Explorer, and Chrome. So we wanted to come up with a solution that would work against all of them. And so we decided to get rid of initial issue of this problem, that is integer constants in JavaScript. Therefore, our approach is rewriting the JavaScript code to get rid of all the integers there. So this is as simple as whenever we see an integer constant, we replace it with a global object. And then we pre-initialize this global number at the beginning of the source file. And now, instead of inlining this embedded value into a native code, the code that is supposed to read the value of some memory address will be compiled. However, we also have to deal with implicit type conversion here. That is, in JavaScript, whenever we have, for example, a string literal, which contains number representation and is used in either bitwise or arithmetic operation, JIT-compiler will assume the type of this string literal to be a number. It will implicitly convert it, and then optimizing compiler will try to inline it inside. And to deal with this issue, we simply have to tell optimizing compilers that we are interested in a string object and not a number. And in our case, we simply do it by calling toString method on this string constant. So our implementation of rewriter is inside the proxy, and we decided to go with the proxy implementation because we wanted to test our solution on different browsers. However, for more efficient implementation, one can also implement it as an extension or a browser plugin, which also will allow us to target specific browsers separately and gain more performance out of it. And in our rewriter proxy now, we distinguish between what to rewrite, and we take JavaScript from either imported libraries, inline JavaScript between script tags, or event handlers on HTML tags. We also have to deal with dynamic JavaScript creations, that is functions such as eval or setInterval, which are able to take string as an input and generate JavaScript out of it. To deal with it, we use function hooking. We hook all these functions, and every time they are called, we first rewrite the JavaScript on the proxy side, and then we call the original function with rewritten JavaScript. And finally, DOM modification. Whenever a new node is added, for example, to a DOM tree, we have to scan if it actually contains a JavaScript. If it does, we rewrite it also, and then we append it to a parent. We have manually verified that all these modifications got rid of all the constants that we found in the first case. However, it comes with a cost, and the cost is coming from two different places. So one is the runtime of the JavaScript, and another overhead is also rewriting time of the JavaScript libraries itself. And to measure the runtime overhead, we used Octane benchmark, and it showed 23% performance decrease in Chrome and 24% performance decrease in Edge. And to measure rewriting time, we used two popular JavaScript libraries, AngularJS and jQuery. And measured rewriting time it took for us to rewrite them. And their minified version took 63 milliseconds and 51 milliseconds for AngularJS and jQuery. However, this cost is paid only for the first time we do rewriting, because after that, these libraries can be fetched from the cache. So to summarize my talk, today I have shown that JIT engines and JIT compilation are a perfect chance for attackers to do code injection attacks. And although browser vendors are aware of this threat, and also they try to defend against it, there are still some cases where not all integer constants are blinded, and this gives attacker a chance to do arbitrary 4-byte gadget injection. And finally, I have shown that rewriting JavaScript can also be a way to get rid of all these issues, and this will also work across different browsers. Thank you for your attention. I will be glad to take your questions.